Good day, everyone. I am Gerald Rectofulgar, and this is our report about the Math 201, which is abstract algebra.
And I am the next reporter, Roland Abel.
Hi everyone, so my name is Isime Surat and I'm the one who report about this topic.
So, you matter until you multiply yourself times the speed of light squared, then your energy. This saying was anchored to physics in solving the speed, mass, and energy. But this is not the topic that we are going to focus on. However, we will know the connection between mathematics and the physics. So again, I am Rolin Abel, and now I am going to talk about the use of group theory and particle physics. But first, I will explain the connection between mathematics and physics in a fundamental level. Second is, I will explain the particle physics. So, to understand group theory, let's talk about the symmetry. What comes to mind? In everyday language, symmetry means balance and proportion. In mathematics, symmetry has more precise definition. It means that an object is invariant or left unchanged under a transformation such as rotation or flip. Consider two simple shapes in the cube and the sphere. Which is more symmetric? In the case of the cube, there are 24 symmetries. With the sphere, since there are infinite number of smudge full rotation number of symmetries. So the sphere is more symmetric than the cube since the sphere has finite number. So now let's move on to the groups. A group is a set of all symmetries of an object. For example, a symmetry group of a cube consists of 24 elements, each of 24 centers. So a group is an abstract mathematical entity that describes an object and constructed from objects' symmetries, not the physical objects. Certain groups are given the specific name, so the groups have also the specific name. For example, the symmetry group of a sphere is O3. So this is the name of the symmetry group. Next reporter, please.
So hi everyone, so my name is Isime Surat. So today I will be going to explain or tackle about the particle physics. So what is particle physics? So particle physics is a study of the fundamental building blocks of our universe, or else it is a branch of physics that studies the nature of the particles that constitute matter and relation. So atoms make up all matter we see. So example of atoms are the protons, electrons, and neutrons. So atoms, this is the word from coming from Greek, which is meaning atomos or indivisible. Then we have quarks. So quarks have 6 different types or flavors. So we have up, down, top, bottom, strange, and charm. But the 3 most common quarks are the up, down, and strange quarks. So what are these up, down, and strange quarks? So protons and neutrons are made out of these quarks. Next, we have hadrons. So what are hadrons? So hadrons are a bound of state of 2 or 3 quarks. So from the proton and neutron are different. As you can see, proton has 2 up quarks and 1 down quarks, while neutron has 1 up quark and 2 down quarks. So what about the strange quark? So let me find out what is strange quark. So strange quark is the lightest of all the quarks, a type of the elementary particle. So strange quarks are found in subatomic particle called the hadrons also. So the replacement symmetries. Symmetries in physics are also abstract. The replacement symmetry means that the chairs could be rearranged without causing a visual difference. So as you can see in the picture, it is arranged in line. So quarks have symmetries like the chair. Also, then the quarks have varying masses. So there is approximate flavor symmetry. So the quark symmetry group is called SU3. So SU3. So SU3, instead of swapping chairs, we can swap up quarks for down quarks. So this would swap neutrons and photons with each other. So SU3 elements move quarks around an abstract three-dimensional space up, then down, and strange quarks. So the three common types of quarks are used in this SU3. So the applying SU3 elements to quarks and hadrons is sometimes called flavor rotation. So a flavor rotation is called. Next.
Okay. So we have a bit of terminology. So the objective of this is there are two types of hadrons. Mesons have two quarks and baryons have three quarks. So let's talk about the hadrons multiplets. So if you're talking about hadrons multiplets, we applied the what is this? The symmetric group, which is SU3 transmissions to hadrons, and they turn into a different hadrons of their combination, which is the outcome has the similarities, and also they have a difference of the properties. So these groupings of hadrons are called multiplets. So multiplets means the resulting of a product of a number of the combining those group or groupings of hadrons. So now let's go to the meson and baryon multiplets. So in meson and baryon multiplets, we have the 8 different mesons that connected by symmetric group 3 transmission. So it has the 8 different combination or the groupings. So they can form an octet, which is 8-dimensional multiplet. So using the symmetric group, which is the combination or the 8 dimensional of the baryons like protons and neutrons. So we can also find another transformation of the new baryon. So okay, next. So this is the figure 1, which is the example of baryon multiplets. So next. So now let's talk about the baryons multiplets. So in baryons multiplets, we have to apply those procedure to a certain yields of decuplet and in 10-dimensional multiplets. So which it means that those past multiplets has the different dimensional, which start from 8 until 10. So this baryons is when this theory was first proposed, it predict a particle in the baryons the cuplet that had not been found. So it was an omega which is discovered by Nicolas Simeon, which consisted of 3 strange quartz. Okay. So next slide. So in experimental verification, in the past 1964, the omega minus was discovered by Nicolas Samios, which is physicist, and it was the experimental evidence of eightfold way. So which is means eightfold way is the unified theoretical scheme for classification of the relationship between the strong interaction of the small particle or the elementary particle. So in 1969, Maury Gell-Mann won the Nobel Prize in in physics. So this is the experimental verification. So next, so notation as a matrix is rather than the abstract group itself. So an example of this is the one who discovered the omega minus of Nicolas. So he is the physicist that only focus on the particle that is being needed. So that's it.